All right, section 3.4, we're talking a little bit more about the conditional, which was the main topic of 3.3, and statements that are related to the conditional. Where this topic comes up a lot is in math, in particular when we state a theorem. A theorem in mathematics is just a fact, a mathematical fact that has been proven. And oftentimes theorems come in the form of conditionals, if-then types of statements. Any given conditional, any if-then statement, has some important related statements that in mathematics sometimes we ask, is this related statement also true, and can we prove that? So let's talk about them. There's 4 important related statements, one of which is the conditional itself. But if you have a conditional, P implies Q. There is another statement involving the same P and Q, but if we reverse them, if we instead write Q implies P, we call that the converse of this original statement. If we take the original statement and take the negation of P and Q, but don't switch their places, that's called the inverse of that original statement. And then finally, if we kind of apply the converse and the inverse at the same time. So basically, if we switch Q and P in our conditional and then take the negation of each of those, we call that the contrapositive of the original statement. And so let's start by working with a statement that's written in English and come up with the other 3. The statement we're going to be given is a conditional. Let's come up with the converse, inverse, and contrapositive of this statement. So in this case, the conditional is, if it rained, then the ground will be wet. Okay, so we want the converse first. Converse. All right, so here, if it rained. So it rained is the statement P. That's the first, or that's the antecedent. Then the ground will be wet. That's going to be statement Q, our consequent. So what the converse does is it switches the place of the consequent and the antecedent. I would write, if the ground is wet, if the ground is wet, then it rained. Okay, so that's what it means to say, take a statement of the form P implies Q and switch it so that it says Q implies P. The ground is wet is now my antecedent instead of the fact that it rained, and the fact that it rained is now the consequent as opposed to the antecedent. Okay, let's do the inverse next. So the inverse does not trade the places of the antecedent and the consequent, but it does take their negations. So the original statement said, if it rained. The negation of that would be, if it did not rain. If it did not rain. Okay, then the ground will not be wet. We need the negation of then the ground will be wet. So then the ground will not be wet. Okay? Finally, the contrapositive, which is like the converse and the inverse done simultaneously. So we want to switch the order of the 2 statements, the consequent and the antecedent, and then take their negations. So for our contrapositive, we would say, if the ground is not wet, then it did not rain. Okay? So those are your 3 different types of, or different related statements to our conditional. Now, the keyword is related. They are not identical to your conditional. Each one is saying something using the same component statements as your conditional, but it may be that one of these statements could be true while the others, or some combination of the others, could be false. So let's think of the first statement for a second. If it rained, then the ground is wet. That's a reasonable condition. We can assume that that would be true because, again, if it does rain, where does the rain go? It falls on the ground and it makes the ground wet. That's a reasonable assumption, a reasonable thing to be considering true. Is the converse necessarily true? If the ground is wet, then it rained. It turns out that by switching these two, the antecedent and the consequent, we get a statement that's not necessarily true. Because if the ground is wet, does that necessarily imply that rain is what made it wet? That's not necessarily true. The ground could be wet for other reasons. Maybe somebody sprayed a hose on the ground and that's what made it wet. So the converse in this case is not necessarily true, even though the original statement was true. Is the inverse necessarily true? If it did not rain, then the ground will not be wet. Well, again, kind of by the same logic as up here with the converse, we could say that this is not true necessarily either. If it did not rain, does that mean that the ground will be dry? Another way of saying not wet. No, that's not necessarily the case, because again, there are other ways that the ground could have become wet. So this statement does not necessarily imply the consequent. The contrapositive, let's look at that. If the ground is not wet, then it did not rain. I would suggest that that actually is true if the original statement was true, because again, if the ground is not wet, is it possible that it rained? Well, if we're going to assume that the original statement is true, then no, that couldn't be the case, because if we think that this consequent is false, then that would imply that it did rain. But if it did rain, then the ground couldn't be dry, like we're suggesting in the antecedent. So it looks like the contrapositive would have to be true when this conditional statement, original conditional statement, is true. Now that's just the case for this one example, but it turns out that that's actually going to be true in general. In other words, any conditional will be true anytime its contrapositive is true and vice versa, and any conditional will be false anytime its contrapositive is false. And that's what it means for these two statements to be equivalent. So the conditional is equivalent to the contrapositive, meaning they're essentially, we can consider them the same statement even though they could be phrased very differently. What we want to do is show that, though. We sort of made an argument here, but in order to show that two statements are equivalent, we need truth tables for them. So let's remind ourselves of what the truth table for the for the conditional is. If P, then Q. Okay, so we have P, Q, and then we have P implies Q. Let's go up here. True, 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 false, false, true, false, false. Okay? Remember, with the conditional, we spent a lot of time in section 3.3 talking about this. The only time it's ever false is if you have a true statement implying a false statement, since that can't happen. In all other cases, we have true. Okay? Now, let's look at the contrapositive. I could write the contrapositive this way. If not Q, then not P. Okay, so this truth table is going to look a little bit bigger because I have P and Q, but in my contrapositive, I also have the negation of both of those. So I'm going to need not P and not Q as well. And then finally, the contrapositive, which looks like not Q, implies not P. So this one has 5 columns. Okay, same combination of truth values as always for my P and Q. True, 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 false, false, true, false, false. Okay, using the negation to get the opposite of these truth values, not P will look like FFTT, or false, false, true, true. Here I have true, false, true, false, so we're going to have false, true, false, true. Now let's take a look at which direction this conditional is going. It's not Q implies not P. That's the 4th column implies the 3rd column. And again, it's easiest to just handle the single case where we have a false conditional. That's when true implies false. Notice that's only happening here. True implies false. So I'm going to get false there, true everywhere else. And even though this table is bigger, it has more columns, the only thing that we're looking at is this last column to determine whether or not these two truth tables are equivalent, because we kept the P and the Q the same. True, true, false, false, true, false, true, false. For every combination of these columns match. Okay, so those two statements are equivalent. Now, it turns out that those are not the only equivalences in these related statements. The converse and the inverse are also equivalent to each other. So in other words, if I have a conditional statement, P implies Q, and then I determine what its converse is, Q implies P, and its inverse, not P implies not Q, then the converse will be true anytime the inverse is true, and vice versa. The converse will be false anytime the inverse is false, and vice versa. That makes those two statements equivalent. We could prove that using truth tables like we just did, but it would look very much the same as what we have here, and so we're not gonna bother with that. Okay, so that's kind of what I'm talking about up here, the equivalence of these statements. All right, now to kind of see a little bit more clearly why we don't necessarily have all four statements being equivalent. For example, why is the conditional not equivalent to its converse? And we sort of saw that with the example that we looked at before, but let's look at another example that's a little more mathematical. If a number is divisible by 4, then the number is even. This is a mathematical fact. Every number that's divisible by 4 is guaranteed to be even. We know this, it's easy to prove. So this is a true conditional statement. But let's look at the converse of this statement. Remember, the converse just switches the antecedent and the consequent. So the converse would say, if a number is even, then the number is divisible by 4. And this is false in general. Even though many even numbers are divisible by 4, if we can find any number that's even but is not divisible by 4, that proves this statement false. And the number 6 is one such counterexample. 6 is an even number, but it's not divisible by 4. Okay? So a true statement here does not mean the converse is also true. Okay? I should point out, and we're going to address this more in a little bit when we talk about the biconditional. It's not necessarily that the case that a conditional and its converse are always have opposite truth values. It is common that a conditional statement and its converse can both be true at the same time. But these examples serve to show that you can't just assume that's the case. All right? So here we have a conditional statement, P implies not Q. And what we want to do is find its converse, its inverse, and its contrapositive. Notice we're given a statement in symbolic form, so our answers are going to be in symbolic form as well. So we just need to remember how to do this. What is the converse? Well, the converse takes a conditional statement and switches its antecedent and consequent, but does not change any of the or doesn't take the negation of anything. So this P is going to end up over here, and this not Q is going to end up over here. Not Q implies P. Notice I didn't take any additional negations. The only reason there's a negation here is because it was already there to begin with. What about the inverse? Inverse doesn't change the antecedent and consequent, but it does take their negation. So I'm going to have not P implies not Q. But as we've seen before, if you have a negation of a negation, those two negations cancel out, and I just get Q from that. Finally, the contrapositive. For the contrapositive, I want to begin by switching the antecedent and consequent like we did here for the converse. And then I go an additional step of taking the negation of each of those. Q implies not P. So those would be the three related statements to this specific conditional. Okay? All right. This is a relatively short section. We don't do a whole lot of truth tables and stuff in this section, so we're going to get through this fairly quickly, I think in one video. What I want to talk about next is something we've already kind of addressed, but I want to be a little bit more comprehensive about it, a little bit more complete. So we've talked in section 3.3 that a conditional statement, P implies Q, when written in English, can be written in a number of different ways. So sort of the default way of writing a conditional statement is if P, then Q. But there's a lot of other ways of translating that. So for example, we saw that sometimes we can remove the word then, and we still have a conditional statement, if P, Q. If a number is even, it is divisible by 4. Notice I can take the word then out, and it doesn't really mess with the grammatical structure. This is one we've been using a lot. We can also say P implies Q. That's equivalent to if P then Q. One we haven't used yet, but is also very common in math specifically, is P only if Q. So a number is divisible by 4 only if it is even. That's another version that we can use. P is sufficient for Q. This is common in math as well. Same with the next one. Q is necessary for P. I want you to notice here that when we use the word sufficient, the order of these component statements, P and Q, is the same as it would be in the if-then version of that statement. But if you're going to use the word necessary, they switch places. And you might need to think a little bit about how we use these words sufficient and necessary in common language to kind of see why the order needs to switch here. But I'm going to let you ponder on that. This one here is a quantified statement. This one we can't always use as a replacement for if P then Q, because it needs to be a case where a universal quantifier actually makes sense. Sometimes it doesn't make sense. All P are Q. That would have worked in this previous example up here. So if you notice, if a number is divisible by 4, then the number is even. A way of using that other version is to say all numbers that are divisible by 4 are even. So that would be like this version of that statement. And then finally, one more example where the order reverses: Q if P. And this one, the order is reversing, but notice the if moves with the P. Normally we write if before P, and here we're still writing if before P, but the Q is actually coming first. So again, a number is even if it is divisible by 4. That would be like writing that statement in this form. So let's practice this. We want to give 2 different translations of this conditional statement. If you can jump, then you can swim. That's ridiculous, of course. Being able to jump doesn't necessarily imply that you can swim, but remember, these conditional statements could be true or false. This is one that's just false, and we can still do stuff with it, even if it's not a true statement. So here, you can jump would be P, and you can swim would be Q. So I want to just come up with 2 different translations, something other than if P then Q. So for example, if I wanted to do the implies, I do have to change grammatically how I write this a little bit. So instead of saying you can jump, I might say something like being able to jump. Being able to jump implies you can swim. And we've seen this before, but it's just worth mentioning again. If you're going to use a different form of the conditional to make things work out in English, which has a lot of weird rules, you do have to sometimes change the wording of your component statements without losing the meaning of them. So here's one example that we could do. Let's pick a different one. Notice in this one, the universal quantifier doesn't really make sense. Maybe there's a way to construct this in this form, but it doesn't kind of roll off the tongue very well. Let's try one of these ones. Maybe this one where the Q and the P switch places. Q is necessary for P. So again, I'm going to have to change the grammatical structure of it. Q is going to come first. Being able to swim is necessary for being able to jump. And again, is that statement true? No, that's ridiculous. You don't need to be able to jump to be able to swim. But the original statement wasn't true, and these 2 things are equivalent, so it wouldn't make sense if one is true and the other is false. It's just another way of saying the same thing, okay? So that's a little bit on translating those conditional statements into English. Last thing we want to talk about is something that occurs a lot in math, and it's something called the biconditional. There are a lot of statements in mathematics that come in the form of 2 conditionals: if P then Q, and if Q then P. Or in other words, a statement that implies that a conditional and its converse are simultaneously true. I mentioned this before. Even though we looked at examples where a conditional statement was true and its converse was false, I said that that's not necessarily the case. We just don't get to assume that they're both true. But there are many cases where both are true. Here's an example. If a number is divisible by 2, then it is even. This is a fact. It's a mathematical fact. But the converse of this mathematical fact, the converse of this conditional, is also true. If a number is even, then it is divisible by 2. And I didn't write the then, but remember, you can leave it out and it still means the same thing. The reason this is true is because this is actually a definition. The definition of a number being even is exactly this, a number that is divisible by 2. So it's going to work both ways. Those types of statements where you're stating that a conditional and its converse are simultaneously true are called biconditionals. Bi means two, and what that's saying is that the conditional goes two ways or both ways. Okay? The notation for that, and it makes sense why this would be the case, is this: P double-sided arrow Q, implying that the implication goes both directions. Now, writing a biconditional in this form is really cumbersome. It's a lot to write, and we don't typically write it that way. Instead, what we do is we swap out this larger statement here with a short phrase, if and only if. If you ever see that, if and only if, those 4 words in that sequence, that means that you're looking at a biconditional. So in this previous statement up here, I would write a number is divisible by 2 if and only if it is even. That's what means we're looking at a biconditional. Okay? In mathematics, in higher mathematics, where we do a lot of proof and things like that, and we analyze statements of this form, we end up writing if and only if so often that it tends to be convenient to have a shorthand for it. So you sometimes see IFF, and that's not if. You know, it's if and only if. That's what we mean when we write this. Okay, so we could shorten this up even a little bit more by swapping the if and only if out for that shorthand, if IFF. Okay. Now, because the biconditional is a logical connective, we do need to come up with a truth table for it, like we've done for all of our other logical connectives. And the way that we're going to do this is take this original statement up here, if P then Q, and if Q then P, and write that in symbolic form. Remember, we have a logical connective for and. That means that we're looking at a conjunction. P implies Q, and Q implies P. Symbolically, that would look like this. Okay? So what I want to do is come up with a truth table for this. P, if and only if, Q. Okay? But in my truth table, instead of writing this, I'm going to try and come up with this, since these two things are equivalent to each other. So I need P, I need Q, I need P implies Q, I need Q implies P, and then I need P implies Q, and Q implies P. This will be the truth table that I want. All right? Same combination. True, 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 false, false, true, false, false. Okay? Again, remember for conditionals, the only time a conditional is false is if you have a true implying a false, which we have here, which means we would have true everywhere else. Q implies P uses the same 2 columns that we just used for this, but going the opposite direction. Where do I see a true implies false going from right to left? I see that here. True implies false. That would be false. That occurs nowhere else, so we have true everywhere else. Finally, this conjunction is taking the conjunction of the previous 2 columns. P implies Q and Q implies P. That's here and here. Remember, conjunctions are only ever true if both statements are simultaneously true. That only occurs up here and down here. In the other 2 rows, I have a false statement showing up, so those would be false. Now think about this for a second. This makes a lot of sense. If a biconditional is going to be true, then in a way you're saying that the statements P and Q are the same, saying the same thing, maybe phrased differently. We call that equivalent as well. So in other words, if P and Q are always simultaneously true, you would want the biconditional to be true. And if P and Q are always simultaneously false, you also want the biconditional to be true. In other words, as long as P and Q always have the same truth values, the biconditional should be true in those cases. If P and Q have differing truth values, then they can't be equivalent, and you would want your biconditional to be false in those cases. So to wrap things up, let's do an example where we're going to determine whether some given biconditionals are true or false. 2 plus 3 equals 5, if and only if 3 is less than 9. Now, even though these two statements are both mathematical, they don't seem to have any relationship to one another. They seem independent. The fact that this is true, and it is true, of course, does not really have any bearing on whether or not this is true. But this is true. I mean, 3 is less than 9. So we have true if and only if true, which according to our truth table should give us a truth value of true. And again, the fact that these two statements seem independent of each other is not what's important, because remember, we said in a conditional, and because biconditionals are a combination of two conditionals, we said that conditionals don't imply a cause and effect relationship. This is not causing this, and this is not causing this, but they always have the same truth values. Here's another one. The moon is larger than the sun if and only if the earth is flat. Is the moon larger than the sun? Objectively, we know that it is not. So that is a false statement. If and only if, so there's my biconditional, the earth is flat. Is the earth flat? I've addressed this one before, even though there's a number of people out there who shockingly still believe the earth is flat. They're completely wrong. It's objectively true that the earth is not flat. So that is a false statement. Now, don't get thrown by the fact that we have false and false. That doesn't mean that the biconditional is false. It just means that the two component statements always have the same truth value, and in those cases, biconditionals will come out true. Okay? You can confirm that in our truth table here. Finally, the letter E is a vowel, if and only if the letter O is a consonant. Is the letter E a vowel? Yes, it is. That is a true statement. If and only if the letter O is a consonant. That is false. The letter O is a vowel. So here we have true if and only if false. Differing truth values, which makes my biconditional here false. Okay? That's going to wrap it up for 3.4.